7. Monitors. By using semaphore mutex, we solve the critical section problem, ensuring the mutual exclusion assigns for sharing data. We know that we use the mutual exclusion semaphore in this way. First, we use wait mutex. That means the application program or application progress require the resource from the system. If there is no resource free, then the application progress call wait operation will be put into the waiting queue for the semaphore. Okay. Now, after finish critical section, he will release the resource by signal operation. So like this. Suppose that a precise interchanged order in which the wait and signal operations on the semaphore mutex are executed, resulting in the following execution like this. In this situation, several processes may be executing in the critical sections simultaneously, violating the mutual exclusion requirement, because the signal operation will not cause any application progress called the signal system call will not be put into waiting queue. Okay, so any progress can pass this signal operation and enter its critical section. So this, however, may be discovered only if several processes are simultaneously active in their critical section. Okay. So to deal with such errors, we introduce a fundamental high-level language synchronization construct, monitor. First, monitor usage. Monitor. A monitor type is an abstract data type that includes a set of programmer-defined operations that are provided with mutual exclusion within the monitor. The monitor type also declares the variables whose values define the state of an instance of that type, along with the bodies of functions that operate on those variables. The syntax of a monitor type is shown here. Okay. The representation of a monitor type cannot be used directly by the various processes. Thus, a function defined within a monitor can access only those variables declared locally within the monitor and its formal parameters. So we can see here there are variables and also the procedure that operated on the variables. Okay. Similar, the local variables of a monitor can be accessed by only the local functions. The monitor construct ensures that only one process at a time is active within the monitor. Consequently, the programmer does now need to code this synchronization constraint explicitly. Okay, so we can see here like this schematic view of a monitor. So a monitor is like a box. Okay, within this box there are shared data and various operations that operated on the shared data. Also, there are initialization code, okay, for the data, for the shared data. So any process that want to operate the shared data must call the operation within the monitor. So this this constructor ensures that only one process, application progress, can operate anytime. Only one process can operate on the shared data. Okay, so it ensures a mutual exclusion operation. Okay, so however, the monitor construct as defined so far is not sufficiently powerful for modeling some synchronization schemes. For this purpose, we need to define additional synchronization mechanisms. These mechanisms are provided by the condition struct. A programmer who needs to write a tailor-made synchronization scheme can define one or more variables of type condition. Okay, so like this. Okay, and the only operations that can be invoked on the condition variable are wait and signal. So the operation x.wait means that the process invoking this operation is suspended until another process invokes x signal. The x signal operation resumes exactly one suspended process that waits this condition. If no process is suspended, then the signal operation has no effect. So monitor this condition variable here. In this scheme, we can see that there are two conditions, x and y. So also there are processes waiting in the queue, that means suspended on the condition x and y. Okay, so also here there are processes waiting enter into the monitor. Okay, waiting for entering into the monitor. Okay, so